Thank you. So yeah, my name is Jiri Kremser. I work for Red Hat. And today I'll be talking about analyzing blockchain transactions using Apache Spark. Here is outline. I will say what blockchain is. I guess most of you are here because there was a blockchain in the name of the talk and it's totally overhyped. But I will focus on the tech side, no marketing bullshit, so it's very then I will talk how to convert a blockchain to graph. The next section will be like how to tackle the graph from the Spark perspective, and almost half of the talk will be live demo, so bear with me. So what blockchain actually is? For me, it's a distributed ledger system, linked list of blocks, where each block contains some information. I will show on the next slide. And it uses heavily cryptographical principles like hashing algorithms to assure that the mining nodes spend some time on the process called mining. So as you can see, is a linked list where each block has a link to the previous one. So here is what block actually is. It contains, it's addressed by its hash number, and as you can see at the beginning of the hash, there is a couple of zeros, and it means that during the mining, the miner had to guess the number, which was, after hashing the whole block, it was lower than some threshold called difficulty, and if the miner succeeded, he was rewarded by, today it's 12.5 bitcoins. That's the incentive for the miner to do the mining. It also, the main reason is to contain all the transactions in the block, but it also has something called the magic number, which denotes the flavor of the bitcoins of the blockchain, because these days you can have Bitcoin blockchain, Ethereum blockchain, and other coins. Each of them has its own implementation of blockchain. Sometimes there are small differences, sometimes there are bigger differences. And if it is like forked original Bitcoin, it's determined by this magic number. It also has something called hash Merkle root, which is a hash of all the transactions contained in this block. And these days there is a hard limit, 1 meg for each block, so you can't put more transactions than 1 megabyte to a block. So what actually a transaction is, as I said before, it's stored in a block, but technically it's a list of inputs and outputs, where there is a simple equation, this rule that sum of all inputs must be higher or equal to sum of all outputs. You can't spend more than you have, basically. And also you have to have all the private keys to all the inputs. You have to own the wallets or own the addresses from which you want to send the money to someone. So as I said, the confirming of the transaction is finding the right nonce, which is a random number that is combined to all the transaction in a block after hashing is small enough. So if, for instance, Alice wants to send a couple of bitcoins to Bob, he said he has nothing. She will create a new transaction, and she says that from her input address, there should be 0.2 bitcoin sent to Bob, and the rest she will send to herself. It's kind of tricky, because normally you will just send fraction of your balance to someone else, but here we have to satisfy this equation, so she will basically send the rest to herself. So as you can see, Bob is sad, but after the transaction is confirmed, he is happy. This is happy Bob. And this is more complex example of transaction, because it can be there can be multiple inputs and multiple outputs. So it's not always as simple as the original case. Just to be aware, once we see the transaction in a graph, that there can be edge cases. This is called end-to-end transaction. So what I did, I used open source library and created something called Apache Market Converter, which takes blockchain binary data and creates a couple of Parquet files that can be loaded by Spark, and you can use the GraphX or GraphFrames libraries on top of that. So originally I used this approach. I linked all the inputs to all the outputs, so it ended up in this bipartite graph where I had a combinatorial explosion of the edges, which wasn't good. But ideally, I wanted to end up with this kind of network of who sent money to whom. Then I used different approach. I encoded the transactions also in the graph. So I don't have only addresses in the graph, but also transactions and blocks. This is more suitable for querying the data because I can ask questions like who participate in this transaction and send money to whom. So how can we work with graphs in Spark? There is something called GraphX, which is part of Spark core, I think. And it uses RDDs, and it's kind of lower level than GraphFrames, which is based on data frames. There is a lot of built-in functions, such as label propagation. You can run PageRank, but you can also implement your own using something called Pregel. And it's kind of declarative API where you specify how each node should communicate with neighbors. And there's also, in GraphFrames, there's also something called Motif, which is a querying language inspired by Neo4j language called Cypher. I will show you it later in notebooks. Part of the demo will be also showing how you can run Spark on OpenShift, and also this notebook, how you can deploy them to the OpenShift. OpenShift is feature superset of Kubernetes. You may be familiar with Kubernetes. We on Red Hat try to productize the Kubernetes and call it OpenShift, but all you can see can work also with Kubernetes. With Kubernetes, you've got scaling for free because spawning a new pod is really basic operation there. In Red Hat, I work on project, amongst other, called Oshinko CLI. This is a CLI tool that can spawn a new Spark clusters or delete them or modify them or scaling them. We also create a couple of source-to-image builders that can help data scientists to build intelligent application because they don't have to focus on infrastructure, but they can only write a code, and the source-to-image builder creates a Spark cluster for them and containerize their application and deploy everything to OpenShift. I also implemented something called operator pattern last couple of days. It's a design pattern in Kubernetes where you basically leverage this loop, observe, analyze, and act. And you use native objects in Spark, like deployment configs and others. And this operator watches for changes of these objects. And if it sees a new config map, it will create a new Spark cluster. I will show that on demo. There is also effort called Spark on Kubernetes, which uses Kubernetes as native scheduling mechanism. I'm not going to show this because as far as I am aware, currently it doesn't support client mode, and I need client mode for running the notebooks. And also I think that the PySpark is not there yet. So yeah, demo time. Let me run this couple of these commands, and I will command them what they do. First, I will need to create a new project in my OpenShift. So this is the OpenShift web UI. I can control it here in UI, but I can also use CLI. So I've just created a new project. And here it is. And now I will copy paste these commands. Oops. And shortly, you should be seeing here a new pod spawning. Yeah, the first command creates that operator instance, and the operator watches for a new config map. So in the next line, I'm creating a config map with a couple of metadata in it. It says how the cluster is named, how it's called, how many worker nodes are there, and which custom worker image it should use. Oh, well, it uses this image for workers and also for masters. I use my custom image because I've got data in it. Here in this command, I'm deploying a new, oops. Can you see the demo? No. I'm sorry. This isn't my presentation at all. Oh yes, sorry, I hit some button. Thank you. Not sure what you see and what not, but so I basically copy-pasted these commands to the command line, and now I'm able to see the running cluster in OpenShift. There is one master and 2 workers, and one instance of a blockchain notebook. So if I open the blockchain notebook, this is the Jupyter notebook. Let me try to make it more visible by putting in a full screen. And I will also get rid of table of contents and toolbar. So as you can see, if I evaluate this cell, it should report that it's connected to a cluster that's running in OpenShift, not on my local host. And I'm loading these Parquet files I was talking about before. So I've got one Parquet file for addresses, one for blocks, one for transactions. These represent the nodes in the graph. I will merge all these data frames together, adding some discriminator column to it. Also load the edges and create a graph frame representation of the graph to be able to work with it. Here I calculate the degrees of the nodes, basically how many edges are pointing to me or out of me, and calculate some basic statistics and aggregate by the type. So that we should see some average degree for transaction, for block, and for address. This is A, B, T. And some was the standard deviation and so on. So for instance, the block, the in degree is 1. It makes sense because to block there is only one edge, and this is the previous block. Like each block is referenced by its successor. Sorry, the next block. Here is an example of a motif query. So as you can see, it's ASCII-based query where you describe like which node points to which node, other node, and then apply some predicates to those edges or nodes. Here, for instance, I'm finding some transactions that happen within some time window and were smaller than 10K satoshis. Yeah. Here I will try to visualize some subgraph of the network. And by the way, I'm not working with the whole blockchain. I'm running only the fraction of the whole blockchain to make the demo feasible. But the algorithm this notebook should work also with the whole blockchain. So here I was evaluating something that takes some transaction that's in the first 1,000, and I'm trying to visualize it with a library called Sigma.js. And as we can see, here it is. There was one out input to the transaction, and these red dots are outputs. So these are the addresses where this transaction contributed. Recently, I've discovered a library called, sorry, I make it bigger, called Force Graph 3D. I asked the author to showcase it here, and he agreed. So it uses the force algorithm, and this is the same graph as shown here, but it's in 3D. It also support VR, but I don't have VR set here, and you saw the VR on the keynote already. So here, for instance, I will use the same displaying algorithm, the forced graph 3D, for showing the address, which is according. First, I sorted by out degree, and then I took the biggest 200 biggest one. So if I visualize it, it looks like. Oh no, it's here. First I need to convert it to some JSON data and then pass it to this algorithm. And as you can see, this is some quite complex transaction. Sorry, address. And these red dots are the addresses who contributed to this address, and green ones are the outcome, are the addresses where this address sent the money. And on the edges, I have also information how much money was sent. This is in satoshis. I can also use different address. So, for instance, if I plug different number here, it should show some small address, less frequent address. Oh, it's actually bigger, kind of. It's because I'm sorting according to out degree, but it can have bigger in degree. That's the reason, I guess. So let me run the last cell, and I don't know if my computer will survive, because here I will taking bigger chunk of data, and I will try to visualize like bigger portion of the graph, but it will be really, really slow. But it's a random sample. There is no rule. I just took sample data from all the transactions I had in the data set, and provide, if we were lucky, we were able to see those clusters. But if the sampling was done differently, the edges wouldn't be here. So this is the first notebook. I have also a second one. Let me close this one. This was graph frames. I have also notebook for GraphX. This time I will be running it on my local host, so no OpenShift, because I want to save some time. This time I'm not using Jupyter, but Spark notebook. Again, I will toggle the. Oh, it's turned off. So I will evaluate all the cell, and I will be describing what it does. It's similar at the beginning. So I'm loading nodes and edges. This time I'm working with different representation. I'm not working with this more granular data schema, like I don't have transaction blocks and addresses. I only have nodes, and these nodes are addresses. And edges are the communication between the addresses. So I kind of neglected the abstraction of transactions. Oops. Sorry. As you can see, all nodes contain some prefix, so I have some data cleaning here. I remove the prefix here, the Bitcoin address. And I'm creating GraphX representation by this graph and passing all the nodes and edges. And here I'm running the PageRank algorithm on top of it. I should have short explanation of what PageRank is, but I'm sure you already know in my presentation. So this is the result of PageRank algorithm that was run on this graph. And as you can see, there are quite big nodes called C and B. And this node B is big because it has a lot of incoming edges. But this node C is big because it has a pointer from the node B, which itself is big. So it's an iterative algorithm which converges to some state. And the state denotes like how probable it is if you randomly walk through the graph that you will end up in the node. It was a really vague description, but we don't have time to describe PageRank here. We just run it because it's there, and we can use it for free. and we should be able to discover some interesting addresses by just running it on this transaction graph. Here we can see we calculated the ranks for each node ID. So once we join it with its rank and sort it, we can have the top 10 addresses. And I'm gonna cheat a bit, and I'm gonna call a blockchain info API and pass the address to it. We calculated right here, and I'm gonna collect the information from this service and display it in the notebook. So here are helper functions in Scala that will call the blockchain info API, and I have also some helpers for converting bitcoins to USDs. This is probably old. Should be something like this, I guess. It's changing all the time, right? So if I run it, I can see the detailed information for those top 10 addresses. This is, again, adding some HTML around the results. So here I have a table, and this is sorted by the PageRank. I can see that the highest one has the balance, this amount of USDs, and it has a lot of sended transactions, and the second one has even bigger amount of transactions that were sent. It's a clickable link that should point to a blockchain info, so I can verify its really frequent address. And for the first one, I think it has also metadata. Yeah, the first one is a fish pool. The mining pool is something where people can aggregate to mining pools and mine together and be rewarded together, because it's very unlikely that you will be the one who will mine the block. So people do that to be more frequently rewarded, but with smaller amount of bitcoins. And this metadata is here because the fish pool itself told the blockchain info that it's there. There is no magic in here. Like, everyone is allowed to go to a blockchain info and basically add some tag to your address for the others to. It makes sense because they are public mining pool, and they want to be recognized by other people. But otherwise, it's totally pseudonymous network. Right, so let me switch back to the presentation. That was the GraphX notebook. Yeah, that was basically it. Here, main takeaways is that blockchain is out there. It's open source. You can use graph frames or GraphX in Spark to work with it, or to work with Graph. And what I did here, I used containers to create reproducible experiments, and also OpenShift to run those containers and orchestrate them easily. How to get started? In Red Hat, we work on a project called redanalytics.io. These tutorials are also on this website, so you can go there and play with it. The Docker images are available on the Docker Hub, so you can easily replicate what I've shown here right now. You can use it for your own experiments. And thank you very much, and that's it.
If you'd like to ask a question, please come to the microphones in the center. All right, let's give him one big hand.